All right, once again, if it's hard to understand me, I apologize for my voice. It is just now returning. I wanted to go over section 2 and section 4 with you. This is business calculus, and we're going to start with the differentiation or derivative formulas. All right, so with 3.2, I'm going to share the screen with you. This is the PowerPoint that is on Blackboard. So our basic rules for differentiation 3.2. We want to start with the derivative of a constant. So the derivative of a constant is 0. Remember this ddx is a derivative with respect to x. So the derivative with respect to x of any constant c is equal to 0. It's given that c is a constant. So in example 1, says here are 4 examples of the rule that the derivative of a constant is 0. So for part A, we have ddx of 15. 15 is just a constant, so it's a number. The derivative of any number is 0. For part B, it says if f of t is equal to 1, then f prime of t is equal to 0. So remember, this is just a difference in notation. This is using the Newton notation as compared to the Leibniz notation in part A. But if f of t is 1, then f prime of t will be the derivative of a constant, 1. Derivative of any constant or any number, 0. Part C, ddx of -6 is equal to 0. That's derivative with respect to x of any number. Here, -6 is equal to 0. And for part D, it says if y is equal to the square root of 3, then dy dx, or derivative of y with respect to x, will be equal to 0. Part C and D, just want to bring to your attention that -6, if that constant or that number is a negative, makes no difference. It's still a constant. Its derivative is 0. If the number is irrational, like in part D, the square root of 3. The square root of 3 is an irrational number, but at the end of the day, it's a number. So if it's a number, the derivative of any constant is equal to 0. Next rule that we need to go over is the power rule. Power rule states the derivative with respect to x, or ddx, of x to the nth power is equal to nx to the n minus 1. This is where n is a real number. So this rule is one of very much importance. So we want to bring this to our attention, or at least keep this rule in mind. This is going to be the rule that we use the most. All right, so if we're trying to find the derivative of any x raised to some power n, the easiest way to find that derivative, take the exponent n, bring it out front, and decrease the exponent by 1. So the derivative of x to the nth power, nx to the n minus 1. All right, so in example 2. In example 2, we're asked to find the derivative, and we're given the equation y is equal to x to the 5th. So if y is equal to x to the 5th, we're asked to take the derivative of x raised to some power. Here, this is a good candidate for the general power rule. Remember, x to the nth prime is nx to the n minus 1. In this case, n is 5. So we're trying to find the derivative, or y prime. We're going to take the x to the nth power and make it n x to the n minus 1. Or in this case, we'll have 5x to the 4th power, because 5 minus 1 is 4. So y prime, 5x to the 4. All we did here was apply general power. Picking up where we left off here, example 3. Just switching up the notation a little bit. Example 3 says if y is equal to the square root of x, we're asked to determine dy dx, or the derivative of y with respect to x. Right, so we're given y is equal to the square root of x. First thing that I would do, I'm going to rewrite y as x to the 1/2 power. Remember, there's an algebra rule. It states the nth root of x to the m power is equal to x to the m over n power. Or we can take any radical, square root, third root, fourth root, nth root, and make it a fractional exponent as long as you remember this rule. Just remember that square root has an understood index of 2. And if it doesn't show a power with the variable, it's understood to be 1. So here, the square root of x to the 1/2 power. The reason this is important is because if we apply this, we can now, by introducing that fractional exponent, should I say, this 1/2, we now have an n to use in the general power rule. So when trying to find the first derivative or the derivative of y with respect to x, dy dx, then apply the general power rule, bringing the n out front, 1/2, x to the 1/2 minus 1 power, or we will have 1/2 x to the negative 1/2 power. Remember, we don't want to keep negative exponents. There's another algebra rule saying that a to the negative n power is equal to 1 over a to the positive n power. If we want to get rid of negative exponents, take the entire number, push it to the bottom of our fraction, make the exponent positive. And if it's already in the bottom of our fraction, let's say this was a negative exponent, we push it to the top and make the exponent positive. Say that to say, the dy dx is really 1 over 2x to the positive 1/2 power, or 1 over 2 times the square root of x, because x to the 1/2 and the square root of x, same thing. All right, example 4. Example 4, we have to obtain the derivative of f of t. And f of t is 1 over t to the 1 over t squared. So we're given f of t, 1 over t squared. I'm trying to find the derivative of this. First thing I would do is take advantage of that algebra, the algebra that I brought up before. A to the negative n is equal to 1 over a to the positive n. In this case, as I'm looking at this f of t as a quotient, 1 over t squared, I'm going to rewrite f of t as t to the negative second power. Even though our variables have changed and went from x to t, we're still introducing an exponent, or we can think of this exponent -2 as n in our general power rule. So now we can start working on that derivative, our f prime of t. From general power rule says we bring the n out front, multiply our base by that exponent, and decrease the exponent by 1. So this will give me -2t to the negative third power is f prime of t. We don't want to keep that negative exponent though. So f prime of t will be equal to -2 divided by t to the positive third power. All right, next rule that we're going to go over is the constant multiple rule. Constant multiple rule states that ddx of c times a differentiable function f of x is equal to c times the derivative with respect to x of that function f of x. Or if we have some number, a constant multiple c in front, what we can do is pull the number out front and multiply it by the derivative of the differentiable function f of x. In example 5, we have 2 different functions, y. We have to find dy dx of both using the constant multiple rule. All right, so example 5, part A, we're given the function y is equal to 4x to the 6. And for part B, we're given y is equal to x cubed over 5. All right, so for part A, when we're looking for dy dx, so the derivative of y with respect to x, use that constant multiple rule, or This is technically ddx of 4x to the 6, because that is y. These are constant multiple rules, and this is 4 times ddx of x to the 6. We use our general power rule to find a derivative of the derivative with respect to x of x to the 6. It's going to give me 4 times 6x to the 5th. We're bringing the exponent out front, multiplying by the exponent and decreasing the exponent by 1. And 4 times 6 will give you 24. So our answer ends up being 24x to the 5th power. And this is dy dx, or the derivative of y with respect to x. All right, for part B, where we're given y is equal to x to the 3rd power over 5, or x cubed over 5. All right, so here we're looking for the derivative of y with respect to x, or dy dx. That we get in part A. That's going to be ddx, or derivative with respect to x, of x cubed over 5. Now this is a quotient of 2 differentiable functions. Instead, we're going to look at this and introduce the constant multiple, because x cubed divided by 5 is the same thing as 1/5 times x cubed. Difference is here. Now we can treat 1/5 as a constant multiple. Applying that constant multiple rule, that's 1/5 times the derivative with respect to x of x cubed. Now we can use the general power rule to find the derivative with respect to x of x cubed. That's going to be 1/5 times 3x squared. Remember the general power rule, bring the exponent out front, decrease that exponent by 1. Or our answer ends up being 3x squared divided by 5. And this is the derivative of y with respect to x. Next thing we reminded of is that technically we use the constant multiple rule, general power rule together. Just in case we haven't picked that up. We can have the general formula for it, the derivative with respect to x of some constant multiple x times a differentiable function to n times cx to the n minus 1. Or we can still apply that general power rule, bringing the exponent out front, multiplying by the exponent, decreasing the exponent by 1. So with that understanding, we can say the derivative with respect to x of c times x, that's just going to be c itself. All right, so the derivative of any value in front of x itself, let's just say, for example, derivative of 3x. Now that derivative is just 3. Next one we're going to go over are the sum and difference rules. These are going to seem a lot more complex than they actually are. So in practice, it's not going to seem as intricate as it does right now. So the sum and difference rules are first the sum rule, or the derivative with respect to x of f of x plus g of x, or derivative of the sum of 2 differentiable functions, is equal to the sum of 2 derivatives of those individual functions, or the derivative of a sum is the sum of its derivatives. So if we're taking the derivative of 2 functions, f of x and g of x, namely, we can take the derivative with respect to x of each element in that sum, ddx of f of x plus ddx of g of x. Our difference rule, ddx of a difference, or the derivative with respect to x of f of x minus g of x, will be equal to the derivative with respect to x of f of x minus the derivative with respect to x of g of x. Or the derivative of a difference is the difference of its derivatives. Or we can simply take the derivative of each element in the subtraction problem and continue to work down to find that overall derivative. So derivative of the sum of its derivatives. The derivative of the difference is the difference of its derivatives. So example 6, this is our chance to apply both the sum and difference rules. We're given the function y is equal to x to the 10th power plus 3x. So now technically, if we're trying to find a derivative, we're looking for the derivative of y with respect to x of x to the 10th, or what we'll have to do is take the derivative with respect to x of x to the 10th plus 3x. Taking those derivatives, using the sum rule, that's ddx of x to the 10th plus ddx of 3x. We use the general power rule here. The derivative with respect to x of x to the 10th is 10x to the 9th power plus, we actually just went over this rule. The derivative with respect to x of cx is just going to be c. Or in this case, the derivative with respect to x of 3x would just be 3. So dy dx, or derivative of y with respect to x of x to the 10th plus 3x, 10x to the 9th plus 3. All right, next example. Here, we're asked to determine the derivative of y, which is x cubed plus 4x squared plus 7x, minus 7x plus 1. All right, so we're given this equation, which is a sum and difference in conjunction of differentiable functions. And we can use the rules that we've covered up to this point to find that derivative. Okay. So example 7, we're given the function y, which is x cubed plus 4x squared minus 7x plus 1. We're looking for the derivative of y with respect to x. That's technically ddx of x cubed plus 4x squared minus 7x plus 1. We use those sum and difference rules. And this is the derivative with respect to x of each element in this polynomial. So that's ddx of x cubed plus ddx of 4x squared minus ddx of 7x plus dx of 1. This is our general power rule. That's 3x squared plus general power rule along with the constant multiple rule. That's going to be 8x minus the derivative of 7x is just going to be 7 plus the derivative of a constant is always 0, so we don't have to write that. So dy dx of derivative of y with respect to x, 3x squared plus 8x minus 7. All right, example 8. There are 2 parts to example 8. Part A, we're asked to find the slope of the line tangent to the graph, which is y is equal to x squared plus 5x minus 3 at the point 321. In part B, we're asked to find the equation of the tangent line mentioned in part A. All right, so in example 8, for part A, we're asked to find the slope of the tangent line at the point 321. So first, we want to remember that the slope of the tangent line, or m tan, by definition is the derivative. So m tan is dy dx of our given problem. Now we go back, just want to make sure we understand where this is coming from. We go back, we're given that y is equal to x squared plus 5x minus 3. I'm trying to find the slope of the tangent line at the point 3. All right, so to find the derivative of y with respect to x, we're going to apply the jump power rule, derivative of x squared, 2x plus derivative of 5x, 5 minus the derivative of 3, which is 0. So this is the slope of the tangent line at any point, 2x plus 5. Remember, we're trying to find the slope of the tangent line at the point 321. More specifically, x is 3, y is 21. So we're looking at the slope of the tangent line at that point. This is going to be m tan is equal to 2 times 3 on my x coordinate plus 5. 2 times 3 is 6, 6 plus 5 means that the slope of the line is 11, or the slope of the tangent line at that point is 11. Now for part B, we're also asked to find the equation of this line. So given that we have a point and the slope, it makes sense for us to use the point slope formula or slope intercept formula. Slope intercept, or y equals mx plus b, is the simplest for me. It says since the slope is 11, we'll have y is equal to 11x plus b. Remember that it goes through the point 321, or x is equal to 3, y is equal to 21. So this is really 21 is equal to 11 times 3 plus b, is making the appropriate substitutions in the equation that we had, and we can solve this for b, which will give us the equation. So this is 21 is equal to 33 plus b. Subtract 33 from both sides, and we can get b. Then b is equal to negative 12. So the equation that we're looking for would be y is equal to our slope 11x minus the y-intercept 12. This is our answer for part B. All right, example 9 says given that f of x is equal to x squared plus 4 times the square root of x, we're asked to determine f prime of 11. Like it says in example 9, we're given the function f of x, which is x squared plus 4 times the square root of x. And we're asked to determine f prime of 1. Okay. So in order for us to find f prime of 1, we must first find f prime of x. So that's what we're looking for first. So with me, I'm going to go ahead and rewrite that square root of x as x to the 1/2 power. So I'm going to rewrite f of x, which is x squared plus 4 times x to the 1/2 power. Now we can start working on f prime of x using the general power rule for both elements in conjunction with the sum rule. So f prime of x, the derivative of x squared, 2x, plus 4 times the derivative of x to the 1/2 power, which is 1/2 x to negative 1/2 power, or 2x plus 2 over the square root of x. Because 4 times 1/2 gives me 2. X to the negative 1/2, push it to the bottom of my fraction, make the exponent positive. So this is f prime of x. 2x plus 2 times 2 divided by the square root of x. So we're looking for f prime of 1. This means we're going to replace every x in f prime of x with 1. So this would just be 2 times 1 plus 2 divided by the square root of 1. Or we would end up with 2 plus 2. F prime of 1 equal to 4. Homework for this section, we'll do it on page 119, problems 1 through 19I, as well as 27, 29, 33, 37, 39, 41, 43, and 47. I'm also going to go over marginal analysis with you. I also want to go over marginal analysis with you. Go ahead and share that PowerPoint. All right, so marginal analysis. First definition. All right. First thing we're going to go over is the marginal cost. So by definition, C of x, which is our cost function, that's the total cost of producing x units. C prime of x, or the derivative of the cost function with respect to x, is the marginal cost, or the approximate cost of producing one additional unit. So if we're given costs, that has to find the marginal cost. That word marginal should be a hint word for take the derivative with respect to x. All right. Example 1. It says, suppose that the cost of producing x units is C of x, which is 100 plus 30x minus x squared dollars. This is for x in between 0 and 12, including both 0 and 12 themselves. We're asked to determine the marginal cost when x is 9, or we're looking the marginal cost when x is equal to 9. So given this cost function, 100 plus 30x minus x squared, that's to find the marginal cost. Typically, you'll see a capital MC of x. Now that capital M represents margin. All right, so here, given that C of x is the given function, marginal cost, or capital MC of x, is really the derivative with respect to x, or C prime of x. We know the derivative of any constant, or derivative of 100, 0, plus the derivative of 30x. We know the derivative of cx is always equal to c, so the derivative of 30x would be equal to 30, minus, use the general power rule, the derivative of x squared, 2x. And we're looking for the marginal cost when x is equal to 9. So what we're looking for, c prime of 9. We'll replace every x in c prime of x with 9. So in this case, that would just give me 30 minus 2 times 9. That's going to be equal to 12. Now what, by definition, that marginal cost shows us the approximate cost of producing the next unit. So what this is saying is that after 9 units, have been produced, the cost of producing the next unit which would be the 10th rule, will be approximately $12. Yep. So that's example 1. Example 2. It says a furniture manufacturer determines that the marginal cost of making tables is always increasing. The company decides to stop table production when the marginal cost, I should say reaches, not teaches, I apologize. When the marginal cost reaches $110. Assuming that the cost function for tables is C of X is equal to 0.01x squared plus 80x plus 100. How many tables will the company make before it halts production? So example 2, we're given the cost function, or C of X, which is 0.01x squared plus 80x plus 100. So the marginal cost, or C prime of X, what we need to find, will be 0.02x plus 80. Remember, in this scenario, when the marginal cost reaches $110, this is when we're going to halt production. Remember, like we just said, the marginal cost will be $110. Let's see, prime of X is 110. So we're going to need to solve 110 is equal to 0.02x plus 80. I'm going to waste our time solving that. Showing the steps of solving that. That's going to give us X is equal to 1,500. So we can make 1,500 tables. Then after that, the approximate cost of the next unit will be more than $110. So that's when they'll halt production. So we went over this for marginal cost. So we also can apply this whole marginal concept of a derivative to marginal revenue. By definition, R of X is the total revenue for the sale of X units. Then R prime of X is a marginal revenue from the approximate revenue, R is the approximate revenue from the sale of the next unit. All right. So that relationship holds true for cost, also holds true for revenue, also goes on to hold true for profit. So if P of X, the profit function, which is the revenue function R of X minus the cost function C of X, this is the total profit for the production and sale of X units. So marginal profit, or P prime of X, which will be equal to R prime of X minus C prime of X, or the marginal profit, is equal to the marginal revenue minus the marginal cost. This is the approximate profit from the production and sale of the next unit. So our last example, or example 3, we're going to be asked quite a few things. But example 3 reads, the cost of producing X deep tread radial tires is C of X, which is 4,000 plus 70X minus 0.01X squared dollars. And the revenue from the sale of X tires is R of X, which is 105X minus 0.02X squared dollars. So they give us both the cost and the revenue functions. Cost function being 4,000 plus 70X. minus 0.01x squared, and the revenue function being r of x, which is 105x, minus 0.02x squared. We're just going to handle this one part at a time. So for part A, so determine the marginal cost. Part B, determine the marginal revenue. Part C, determine the marginal revenue of 50 and tell what it means. Part D, determine the marginal profit. And for part E, we're going to find for what value of x is the marginal cost equal to the marginal revenue, and what is the marginal profit in that instance. And so like I said before, it's going to handle it one part at a time. So on example 3, we're given the cost and the revenue functions. Part A, we're asked to find the marginal cost of capital MC of x. We know the marginal cost is really the derivative of the cost function with respect to x. So we're really looking for C prime of x, or the derivative of the cost function with respect to x. So given that this is the cost function, C prime of x, derivative of 4,000, 0, no need for us to write it. The derivative of 70x would be 70, minus the derivative of 0.01x squared, 0.02x. Now here we just use the general power rule. This is the marginal cost function. So we're done with part A. For part B, we're asked to find the marginal revenue function, or the capital MR of x. We know by definition, this is just the derivative of the revenue function with respect to x, or r prime of x. So we're just going to take the derivative of 105x minus 0.02x squared. The derivative of 105x is going to be 105 minus the derivative of 0.02x squared. Use the general power rule, will be 0.04x. So we're done with part B. Part C, we're asked to find the marginal revenue for 50 units, as well as tell what that means. So this is really R prime of 50, because the marginal revenue is the derivative of the revenue function with respect to x. This means we're going to replace every x in R prime of x with 50. So that will give you 105 minus 0.04 times 50. Right, we plug everything into the calculator correctly. That's going to give me $103. And what this represents, this is the revenue from the 51st tire, or the approximate revenue. From the sale, the 51st tire. Keep in mind that marginal is the approximation for the next unit. Part D, we're actually asked to find the marginal profit function. Keep in mind, the marginal profit is a derivative with respect to x out of the profit function. So in order for us to do that, we must first find the profit function, or P of x. Keep in mind by definition that the profit function is the revenue function minus the cost function. In this case, that would give me the revenue function, or 105x, minus 0.02x squared, minus the cost function, 4,000 plus 70x, minus 0.1x squared. All right, keep in mind, we distribute this -1. So we must subtract all three of these quantities. It gives me a profit function, or P of x, is equal to a -0.01x squared plus 35x
minus 4,000. This is what we get when we combine these lifetimes. Now remember, we're looking for the marginal profit function of the derivative of p of x with respect to x. This will be p prime of x, which will give me negative 0.02 x plus 35, the derivative of negative 0.01 x squared, negative 0.02 x, derivative of 35x, 35, minus the derivative of 4,000, which is 0 for us to write. This is our marginal profit function, so we've actually answered part D. And lastly, part E. Let me go back and make sure we got that question right here. So for part E, is what value of x is the marginal cost equal to the marginal revenue, and what is the marginal profit in that instance? So we actually know the marginal cost. Found that out. Previous part of the function. Marginal cost, 70 minus 0.02x. We also know the marginal revenue. Found that in the previous part of the function. That's 105 minus 0.04x. If we take those two equal to each other, trying to find what the x value would be. So we're going to take that 70 minus 0.02x and set it equal to 105 minus 0.04x. Combine our like terms. So give me a positive 0.02x is equal to 35. Adding 0.04x both sides, subtracting 70 from both sides. Then we can divide both sides by 0.2 by 0.02. So give me x is equal to 1,750. So this is the number that will make costs, that we could produce that make costs equal to revenue. The problem goes on to ask, what's the marginal profit in this instance? And so the marginal profit, which will be P prime of 1750, to find the marginal profit in this instance, that would be a negative 0.02 times 1,750 plus 35. We found the marginal profit function in the previous part. We'll replace every x in P prime of x with 1,750. And to no surprise, this means that we made no profit. The revenue is equal to cost. Then there's our break-even quantity, which means we made no profit. We lost no money, but we made no profit. Okay. The homework for this section. Oh, last note, marginal profit is 0, marginal revenue equals marginal cost. So that relationship still holds true. Revenue and cost equal to each other, no profit. This is true through marginal analysis as well. The homework for this section I want you to do is on page 136, which is problems 3, 5, 7, 13, 15, 17, 19, 21, and 23. Oh, I'm sorry, 37 and 41 as well. And I want you to try these problems and the opportunity to ask some questions on these problems. On Tuesday of next week, we'll hopefully be back in the room then. And I'm going to go ahead and go over the homework quiz on Tuesday as well in preparation for our test, hopefully next Thursday. If it's not next Thursday, I'll push it back. I will not move it ahead. So Tuesday is your opportunity to ask questions for 3.2 and 3.4. I'm going to post a homework quiz today, and we're going to go over that as well. So I look forward to seeing you all on Tuesday of next week. Good luck studying.